section 3.3, we're going to look at the product and quotient rules, as well as higher order derivatives. In section 3.2, we learned that the derivative of the sum of two functions is the sum of the derivatives, and we also saw that similarly the derivative of a difference of two functions is simply the difference of the derivatives. That is not going to be the case for either products or quotients. This is very important. So don't write this down. This is entirely incorrect. If we have, let's say, two functions, f of x divided by g of x. This is a quotient, and if we wanted to take the derivative of that quotient, it's most calculus students' wishful thinking that this is going to be as simple as taking the derivative of f and dividing it by the derivative of g, but that's not right. It does not work. Okay. Again, ultimately, if you wanted to derive the rule we're about to see, you would have to go back to the fundamental definition of what it means to take a derivative using limits, work it out, but you do not get the derivative of f divided by the derivative of g. So that's not going to happen. What we do get, though, is, for example, in the product too. Yes, product. The derivative of a product also, again, it's a nice case of wishful thinking here, but this is not true either. The derivative of a product is not going to be equal to the product of the derivatives. Okay, so again, that's a bad calculus. That does not work. So we're going to have two brand new rules in this section. They're going to tell us how to differentiate products and quotients. And the first one is Theorem 3.8, which is the product rule. Let's suppose that we have two functions, f and g, that are differentiable. Then the derivative of f times g of x is equal to f of x times g of x plus f prime of x times g of x. This is how the textbook states it. I typically like to kind of reverse the two terms. I think it's a little bit easier to describe, a little more clear to state, but it's f prime of x times g of x is how I'm going to write it, plus f of x times g prime of x. So to me, the way I describe the product rule is as follows. If you're going to differentiate the product of two functions, you differentiate the first function, so we're going to do f prime, times, leave the second function alone, so multiply it by g of x, plus, this is important, a plus sign in between, now leave the first function alone, don't differentiate it, it's going to be f of x, and then you multiply it by g prime of x. So it's the derivative of the first function times the second plus the first function times the derivative of the second. Let's take a look at example 1. Let's use the product rule to differentiate h of x. And it's going to be very important, especially as we move throughout the remainder of this chapter, that we look at this and we recognize specifically why we need to use the product rule. Here, we have two functions that are multiplied together, and hence the use of the product rule. Albeit, you could multiply these out and distribute it for this one. It won't be too big of a deal and avoid it entirely. But even then, the product rule makes it a little bit simpler. So in this example, the function 3x minus 2x squared is like playing the role of f, and the function 5 plus 4x is like playing the role of g. According to the product rule, it's the derivative of the first times the second plus the first times the derivative of the second. The derivative of 3x minus 2x squared, we know that that's going to be 3 minus 4x, so that's the derivative of f. We're simply going to multiply that to g, so I recopy g down. G is 5 plus 4x, and now plus, now I'm going to leave f alone, so leave the first function alone, and I need to multiply that by the derivative of the second function. The derivative of g, that's the derivative of 5 plus 4x, is simply going to be 4. So this is what we end up with. This is going to be our derivative. From here, we should just kind of go through and simplify it. Here's a binomial times a binomial, so we can kind of FOIL that out. We have 15 plus 12x minus 20x minus 16x squared. For the second term, I can distribute the 4 in. That'll give us a plus 12x minus 8x squared. And so we get as our answer h prime of x. Let's combine like terms and put it in standard order. We're going to have a negative 24x squared. 12 and 12 make 24. Subtract 20 will give us a positive 4x. And then we have one constant term of 15. So h prime of x is equal to negative 24x squared plus 4x plus 15. Let's take a look at the next one. We have y equals x e to the x. Again, the key thing for us at this point is recognizing that x times e to the x is a product. It's the product of the function x with the function e to the x. So once again, we're going to use the product rule. Product rule says we do the derivative of the first term. The derivative of x is 1. Leave the second term alone, so times e to the x. Plus, now we have the first function, x, times the derivative of the second function. Well, the derivative of e to the x is simply going to be e to the x. So our derivative is going to be e to the x plus x e to the x. In terms of simplifying it, this is a perfect way to leave this function, but one of the things that's going to be oftentimes common, and it might be a huge convenience later on, especially when we do higher order derivatives, is even though we can't combine them because the coefficients aren't like out in front, you could still, if you wanted to, factor out the e to the x so that it looks like a polynomial times e to the x. And that's an extremely simple and helpful form to have this thing later on down the road and for applications. But right now this is fine like this. Or if you want to quote-unquote combine like things via kind of factoring it out, you can leave your answer like that too. But either way, this is our derivative for this function. Let's take a look at example 3. In example 3, we want to find the derivative of y equals 2x cosine x minus 2 sine x. So it's hard. We have the difference of two terms. So we know that the derivative is going to be the difference of the derivatives. However, when we go to differentiate this first term is the product of 2x and cosine x. So we will have to use the product rule on this. The derivative of the first part, so the derivative of 2x is going to be 2. Leave the cosine of x alone. Plus, now leave the 2x alone. The derivative of cosine of x is negative sine x. So that gives us the derivative of the first term using the product rule. Minus 2 sine x, even though this is a product, you can think of it as the product of negative 2 and sine of x, but the negative 2 is really just a constant. And so we can really use nothing more than just the constant multiple rule to say that it's going to be the constant, so leave the negative 2, and then multiply it by the derivative of sine, which is going to be the cosine of x. So here's what we have. We have y prime equals 2 cosine x. We can write this as minus 2x sine x minus 2 cosine of x. And then within this expression, our cosine x terms cancel. The positive 2 cosine x cancels with the negative 2 cosine x. And so we get as our final answer, y prime is equal to negative 2x sine x. Okay. Negative 2x sine x. The next thing we're going to look at, this is Theorem 3.9, which is the quotient rule. Let's suppose that we have suppose we have two differentiable functions. Let's call them f and g, such that g of x is not equal to 0. Then the derivative of f divided by g exists, and it's going to be given by the following expression. Again, I like to rewrite it a little bit different than what the book does. I'm going to write it as f prime of x times g of x minus f of x times g prime of x, all divided by g prime of x squared. And in this way, I kind of like it because there's a little bit of symmetry kind of with what's going on with the product rule. Essentially, the quotient rule says the following. To do the derivative of f divided by g, where f is the numerator and g is the denominator, you do the derivative of the numerator times the denominator function. Big difference here. Pay close attention to the sign. Unlike the product rule, there's going to be a subtraction sign in between these two terms. You now take the numerator function, multiply it by the derivative of the denominator, and this whole thing is divided by the original denominator function squared. So it's f prime g minus fg prime divided by g of x squared. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Let's take a look at example 4. We have y equals 5x minus 2 divided by x squared plus 1. Again, the numerator, that's playing the role of function f. That's 5x minus 2. The x squared plus 1, that's the denominator. That's playing the role of g. According to our quotient rule, it should be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. Let's go through and work out each of those pieces. The derivative of the numerator, the derivative of 5x minus 2 is simply going to be 5. We multiply that by the bottom function g, which is x squared plus 1, minus, now we're going to leave the top function alone, so take our f of x, and now we need to multiply it by the derivative of g, derivative of x squared plus 1, that's going to be 2x, and this is going to be all over that original denominator function squared. So it's going to be x squared plus 1 quantity squared. So this is using the quotient rule. From here, we want to go ahead and simplify it. It's typical practice that usually we don't want to expand the denominator. Leave that denominator as it is, it's being raised to the second power, so we're not going to touch that. But let's at least distribute and combine like terms within the numerator. So I can distribute a 5 in. That'll give us 5x squared plus 5. If I kind of imagine kind of bumping this 2x around in front, it's like distributing a negative 2x into this one parenthesis. Negative 2x times 5x is negative 10x squared. And a negative 2x times a negative 2 will give us a positive 4x. Again, keep that all over that original denominator squared. And now just combine some like terms. 5x squared minus 10x squared will give us negative 5x squared. We have our plus 4x, our positive 5, all divided by x squared plus 1 squared. As is often the case, whenever you need to do the quotient rule, our answer will end up being a quotient. And as you probably recall from pre-calculus, this type of, in this case, it ends up actually being a rational function because it's the quotient of two polynomials. You will always want to kind of leave it in simplest form. Oftentimes, that may involve us needing to try to factor the numerator to see if any common factors will cancel with what we have in the denominator. But just be aware that on this one, nothing simplifies. So this will be our final answer. But always be on the lookout, as you're used to from the past experience. Anytime your answer is a fraction, make sure that fraction is in simplest terms and in reduced form. Let's take a look at example 5. We're asked to find the derivative of y equals 3 minus 1 over x divided by x plus 5. So it clearly is a quotient again. We have the quotient of two functions. We could try to go ahead and directly apply the quotient rule. However, it's going to get a little bit sloppy. And one of the reasons for this is that if we look at this function as it is, it's really not in simplest terms because what we have right now is a complex fraction. We have the numerator, which contains the subfraction 1 over x within our main fraction. So let's use our good concept of rewriting this first. Let's simplify this to a common fraction before we try to apply any calculus. Again, many of you might know some different ways to do this. My preferred method is to take the main fraction bar, which is this one right here, and multiply it by the LCD of any of our minor, or what we sometimes call the subdenominators. Here, the only kind of nested or additional fraction levels we have is this 1 over x. So I'm going to multiply both numerator and denominator of our main fraction by x, and that should clear off the complex fraction for us. So if we multiply and distribute this into the numerator, 3 times x would give us 3x. 1 over x times x would cancel, leaving us with a minus 1. And then in the denominator, if we distribute that through, we're going to get an x squared plus 5x. We look at it, this is now a common fraction, there's nothing complex about it, and in this form, it's going to be much, much easier to apply our quotient rule. Okay. So again, no calculus whatsoever quite yet. We're taking that crucial step of rewriting it first. We're simplifying complex fractions, and now we're going to go ahead and we're going to apply the quotient rule. Again, if you're kind of following along, we're thinking of this as like f divided by g, where in that theorem we call f the numerator function, g is the denominator function. According to the quotient rule, we take the derivative of the numerator, that's 3, times the denominator, minus, very important, don't forget that sign is a minus. Now we leave the numerator alone. I multiply that by the derivative of the denominator. The derivative of x squared plus 5x is going to be 2x plus 5. And this is going to be all over the original denominator, whole thing raised to the second power. So this is the application of our quotient rule. It's up to us now to see if we can go ahead and simplify this as much as we can. We have some distribution we can do in the numerator. If I distribute the 3 in, we're going to get a 3x squared plus 15x. Let's expand this part out first. I'm going to keep the negative sign there for the moment. And I'll skip some of this algebra, but you're going to get a 6x squared. The outer and the inner terms would give you a 15x minus 2x. 15x minus 2x would be a positive 13x. And then we're going to have a minus 5, all divided by x squared plus 5x squared. Let's go ahead and distribute the negative sign through in the numerator. We're going to get a negative 6x squared minus 13x plus 5, all divided by x squared plus 5x squared. And now combine our like terms. These two are like, so that's going to give us a negative 3x squared. These are like, that's going to give us a positive 2x. We have plus 5, all divided by x squared plus 5x squared. It's worth checking to see whether or not this would simplify. And in order to check that, we want to factor the numerator. I find that the easiest way to factor that would be to first pull out the negative sign. So we have a leading 1 coefficient. From here, we could try to factor this thing. Factors would be 3x and x. If we had a 5 and a 1, let's see what else. And then we would need to make a negative 2 inner term. So it has to be a negative and a positive. The denominator, it also factors on the inside. Be a little bit careful here. We could factor an x out, and we would have x plus 5 whole thing squared. So the denominator would look like this: 3x minus 5, x plus 1, all divided by, you would actually have an x squared factor and then x plus 5 squared factor. So despite our best of intentions, we try to simplify it. We do get a lot of factorization, but none of the factors end up canceling. So it turns out that this already was our simplified derivative. So y prime is equal to negative 3x squared plus 2x plus 5 divided by x squared plus 5x brackets squared. One of the things that's very important is kind of being adept at working with the rules. And oftentimes there's more than one way to work through these problems, but at the end of the day, efficiency and the best approach should always be the goal. For example, if we look at, this is example 6 part A, we don't even really necessarily need to use the quotient rule for this problem, even though it looks like a quotient. If we, again, first take up the key step of rewriting it first, we can rewrite this as, first of all, x squared over 6 plus 3x over 6. And the reason why we're able to split apart this fraction is because we have a single term in the denominator. And anytime you have a single term in the denominator, that's when you're allowed to split things apart. We can further rewrite this. This is equivalent to just 1/6 x squared plus 1/2 x. And after rewriting it, this makes it extremely easy for us to take the derivative. We have 1/6 times the derivative of x squared is 2x. Derivative of 1/2 x is simply going to be 1/2. And then 1/6 times 2 is just 1/3. So for this one, y prime is equal to 1/3 x plus 1/2. Similarly, in example B, we've done many like this back in the previous section, but this is really nothing more than 5/8 times x to the 4th. So we can use our constant multiple rule, leave the 5/8 alone. The derivative of x to the 4th is 4x cubed. And then 5/8 times 4, that would actually give us 5/2 x cubed. So y prime is equal to 5/2 x cubed. And then we'll look at one more of this section. In part C, we have the following. We have y equals negative 3 parentheses 3x minus 2x squared, all divided by 7x. So on the surface level, it looks like a fraction. It's a quotient. So you might be thinking quotient rule, but again, investigate it a little more deeply. That denominator has only a single term with it. So we should be able to split this fraction apart and completely avoid having to use the quotient rule. I can begin by distributing the negative 3 into the top. That'll give us negative 9x plus 6x squared divided by 7x. We can then, from there, split apart the fraction by writing each term over top of the denominator. And then reducing even further, we are going to get negative 9/7 plus 6/7 x. Please keep this in mind, especially in this class. At this point, for a lot of students in the class, there's a lot of common confusion between, what was the algebraic steps and what is the calculus steps. So far, we haven't done any calculus at all. Everything we've done has been simply just a matter of algebra in order to kind of rewrite it to get it to this step right here. We still need to find the derivative, and now this is the calculus step when we actually apply our derivative rules. The derivative of negative 9/7, that's a constant, so that's 0. And then the derivative of 6/7 x is simply going to be 6/7. Okay. So only at the very end, once we were able to rewrite it and put it into a convenient expression, did we actually then go ahead and apply our derivative rules, which is the calculus-based step of the problem.